Exercise 8.4. We'll do some problems from Q1 and Q2. This section of the book introduces the rule universal introduction. Okay, so most of these problems are going to use that rule. Especially like when your conclusions has a universal quantifier, it's going to have probably going to use a universal introduction. Now, how does it work? Well, you'll notice one sort of strange thing here, and this is something you shouldn't see normally, which is x's or variables without a quantifier. Right? Usually when you get rid of the quantifier, you always have to replace the variable with some letter. So why aren't we doing that here? Well, the variable here is to serve a different purpose. It's to show that you could put any letter in here and the same logic would go through. So let's go ahead and just do this number 2, and I'll talk about it later. So this we get from universal elimination of 1. Right, so we got rid of the quantifier, and we didn't exchange the x's for a's, and like I said, I'll explain that in a minute. Now if we do universal elimination of 2, we're going to do the same thing with the x, keep the x in there. That sets up this conditional elimination, which gives us tx by conditional elimination of 3 and 4. And then this last step is the universal introduction from 5. Now, again, the x's stay in there because the point is to show that you could do the same derivation with any letter we chose, right? So say we decided to replace x with a. We'd get SA conditional TA, SA, TA. Right? If we decide to exchange for the letter B, we'd get SB conditional TB, SB, TB, right? So no matter what letter we put in here, the same exact steps follow. And what that shows then is that for any letter, or put it another way, for all letters, this inference or this derivation is valid, so it ends up proving that everything is a T. Right? If we put A's in here, we would get TA. If we put B's, we'd get TB. If we put C's, we get TC. Any letter whatsoever we can prove is a T. That proves then the conclusion that for all x, x is a T. All right? So again, the reason we keep the x's in there in this case, and this is the only case where you leave the x's in without a quantifier, is to show the universality of the reasoning. Right? No matter what we put in for x, we'd get this same conclusion, which shows that for all x, x is a T. That's what justifies the last step, the universal instantiation or universal introduction. All right, number 4 had a bit of an issue, so I'm gonna. Okay, so we get our first step here by universal elimination of 1. So again, we get rid of the quantifier. We're keeping the x's though because, as you can see, our conclusion is a universal quantifier. So we're going to have to use universal quantifier introduction, and that's the only case where we leave the x's in. All right, now we do the same thing on line 2. That gives us h. It's not going to let me do it here. hx. Let me get that by e2. Okay, so now we can get gx by this biconditional elimination. Oh, the spacing is... Okay, so biconditional elimination, right? If we have a biconditional and we have one half of the biconditional, one part of it, we can get the other part. And then finally, for step 5, we can get all x gx by universal introduction of 4. I don't know why this isn't letting me write these things here, but so line 5 is for all x gx, and we get that by universal introduction from line 4. So again, we leave the x's in to show any letter would work the same way. If we did A, if we did B, if we did C, and that ends up proving that everything is a g. So for all x gx by universal introduction of 4. Okay, Q2 now. This is again not fill in the blank, but you can see our conclusion is a universal quantifier, so we're going to use universal quantifier introduction, and that means we'll just leave in the x's for when we do. Oops, I did this one wrong. This has a third premise. Okay, so we've got this universal quantifier. We've got this is a conditional, right? Now remember, you cannot apply the quantifier rules unless the quantifier is the main operator. What that means is it has to come first. There can't be a negation in front of it, and there can't be another operator outside of parentheses. All right. So in this case, the conditional is the main operator, and that means we can't apply existential quantifier rules to the first part, and we can't apply universal quantifier rules to the second part. Only when the quantifier is the main operator, like in sentence 2, can we apply quantifier rules, inference rules. Okay, but we can get the antecedent of this from step 3. Okay, so we can get some x sx here on line 4 justified by existential introduction of 3. I'm going to move this all down here so it's all on the same page. Okay, now step 5. Now we have a conditional and we have the antecedent of that conditional, so we can get the consequent of that conditional, which is this. So we can get that on line 5, and that's by conditional elimination of 1 and 4. Now this universal quantifier is the main operator in this sentence. So we can do universal quantifier elimination on lines 2 and 5. So let's do 2 first. Not ux or jx. So that's universal quantifier elimination of 2. Then line 7. We can do the same thing on line 5 and get tx, conditional ux, and that's, oops, 5. And again, we're leaving those x's in because we are going to ultimately do, to get our conclusion, a universal quantifier introduction. Okay, so let's do an MC to turn this into a conditional. Ux conditional jx, that's MC of 6. Now we've got the ux's lined up, so we can do a hypothetical syllogism to get tx then jx. That's hypothetical syllogism 7, 8. Now we do one more MC to make it look like that. So that gives us not TX or JX, MC of 9. And then our last step we can do the universal instantiation, or introduction, sorry. So that's universal introduction of 10. So we did this first in order to get this universal quantifier by conditional elimination. Then once we did that, we did these universal eliminations. We kept in the x's because we knew we wanted to do a universal instantiation at the end. Sorry, universal introduction at the end. All right. I'm going to skip down a little bit to number 8 since I only have time for one more. With number 8, we've got 3 universal quantifiers for premises, and our conclusion is universal quantifier. So again, we'll most likely use the universal quantifier introduction. So we'll just go in order. Wx or Cx, conditional Yx or Zx. So that's universal elimination of 1. 2, we get Wx. Universal elimination of 2. We get not Zx. Universal elimination of 3. And again, remember, we're leaving the x's in because we're doing a universal introduction, and we want to show that any letter we put in here would lead to the conclusion that x is a y, and that allows for the last step, the universal introduction. Okay, so how do we do this? Well, our antecedent is a disjunction. We have one of the disjuncts, so we can add the other disjunct by disjunction introduction of 5. That allows us to get Yx or Zx by conditional elimination of 4 and 7. And since we have not Z, we can get Yx by disjunction elimination of 6 and 8. And since we did that all with just x's, we're justified in saying for all x, x is a y. So for all x, yx, and we get that then by universal instantiation of 9. Okay, so again, the idea here is leave the x's in order to show that any letter would work just as well. So we could do this with A's, we could do it with B's, we could do it with C, D, E, F, G, and the exact same logic will work with every single letter we try in here. So that justifies us in saying that all x's are y's. A is a y, B is a y, C is a y, D is a y, etc. So by using the x's, we show that the conclusion is general, that it applies to any letter, and therefore for all x, x is a y. Okay, so that's the important part for universal introduction, is that the same logic could be used with any letter. There's nothing special about any letter that you would happen to use that would lead to the same conclusion. So that shows that for all letters, the same logic applies, and that justifies our universal conclusion.